Now I'd like to do one example unrelated to sort of the work examples that we've done before, um, in which we are interested in understanding why do we care about free energy. And this is a biological example. And what I'm showing here is a series of reactions that are called glycolysis. And I don't understand a whole lot about these overall, but I do want to zoom in on this first reaction here. So we're going to focus on step one, because step one has two reactions that are coupled. And coupled biological reactions are really important because it takes one process that is non-spontaneous, couples it with a process that is spontaneous, and then the combined process can occur in our bodies. For example, so if you start with glucose and you end with glucose 6-phosphate, you have one reaction called the phosphorylation of glucose, and a second reaction called the hydrolysis of adenosine triphosphate, ATP. And you can see ATP to ADP going up here. And so let's look at how these two reactions are coupled, and then we'll talk about what it means to be coupled. So coupled reactions for phosphorylation of glucose are going to start with glucose right here. Glucose is C6H12O6, and here we will consider it aqueous because it's dissolved in blood. Then it's going to react with hydrogen phosphate, 2-, and it's going to make a combined species here, and it's going to give off water. So the rest species will be C6H11O6 PO3 2-. Okay. And this is going to be the glucose 6-phosphate right here. Now hydrolysis of ATP is going to be ATP plus H2O goes to ADP, which is 3-, so this is adenosine triphosphate, adenosine diphosphate. These are aqueous species, and adenosine triphosphate has a 4- charge. And this first reaction has a delta G naught reaction equal to 13.8 kilojoules per mole. So this first reaction does not happen by itself. The second reaction is actually one of the reactions that stores energy in our bodies. Its delta G naught reaction is minus 30.5 kilojoules per mole. And we can do the same thing that we would do for Hess's law, except now we're going to do it for reactions using delta G values. We can see that in this reaction, so the H2O liquid cancels out, and oh, I forgot one of my products over here that I need to cancel out. It's the HPO4 2-. Here, now it balances actually, I apologize for that. And so the hydrogen phosphate ion cancels out as well. That leaves us with an overall process with all of the things that are left, C6H12O6 plus ATP 4-, adenosine triphosphate, goes to glucose 6-phosphate plus ADP 3 minus plus the hydrogen ion. And when you add reactions, you can add delta G values. It's like Hess's law, except delta G. And when you do, you get minus 16.7 kilojoules per mole, and you do get a spontaneous reaction. And so this is spontaneous coupled or overall reaction. And you can see what a coupled reaction means. A coupled reaction has things that cancel out such that the hydrogen phosphate that is a product of one is a reactant in the other. In order for these two reactions to occur together, so they have to have processes like this. The water, not so important because there's plenty of water around, but in order for this process to occur, one must produce a hydrogen phosphate and the other will then use that hydrogen phosphate. And so what makes reactions coupled? Well, one, when species cancel out of the overall reaction. Well, it could be a species, but when some species, A species, cancel out of overall reaction. And in fact, that's what makes the reactions coupled. That's how, so they have to occur together. And when they occur together, you get to add their free energies. That's how non-spontaneous reactions are caused to happen in the body. And then my other note here is that Hess's law works for adding and subtracting delta G values, or so adding and subtracting reactions and their delta G values. Pretty cool.